The last topic we want to look at in Chapter 14 is acid-base properties of salts. A salt is just a very general term for an ionic compound, and often you would think that just ionic compounds would be neutral. If I have an ionic compound that doesn't have hydrogen or hydroxide, we assume it's neutral, and some of them are. Neutral ionic salts will occur when you have the cation from a strong base. Okay, so cation is the positive ion from a strong base. So good examples might be things like sodium from sodium hydroxide, or potassium from potassium hydroxide. Those would be cations from strong bases. And then we need to bond that with the anion from a strong acid. So the anion would be the negative ion from a strong acid. So good examples might be something like nitrate from nitric acid, or maybe chlorine from hydrochloric acid. All right, these would be some good examples. So let's combine them together and make an ionic compound that might look like this. Maybe, so completely neutral. Something like sodium nitrate or potassium chloride. Or obviously it could be like sodium chloride, potassium nitrate. Sodium and potassium are aqueous with everything. So they don't have the ability to produce hydrogen, obviously, but they're also not going to remove hydrogen from the solution. Same kind of deal with nitrate and chloride. They're almost 100% aqueous with everything. Chlorine will precipitate with a few ions like lead and silver, which we're obviously not dealing with here. So if these ions are 1,000,000% aqueous, they obviously don't produce hydrogen, and they're not going to remove hydrogen from the solution either, because hydrogen, nitrate, is so aqueous. Hydrogen, chloride, is so aqueous that the ions stay separated. So all of these four ions have no chance of increasing the hydrogen concentration, which would make them act like an acid, and they can also not remove hydrogen, which would make them act like a base. So you put them together, boom, the solution is 1,000,000% neutral. Okay, so now let's think about solutions that might be slightly basic. Salt solutions that might be basic. A good example is something like sodium acetate. In a solution of sodium acetate, the major species would be sodium ions. Anything with sodium is 100% aqueous, so the sodium and acetate would completely dissociate, H3O2 minus, and if it's in solution, there's obviously water present. So we think about these ions and we ask ourselves, can any of these particles produce hydrogen? Can they act like an acid and increase the hydrogen concentration? And our answer is probably no. Obviously, sodium can't produce hydrogen, and the acetate ion is very, very stable. It's not going to further dissociate and form hydrogen ions. Water can produce a very small amount of hydrogen, but it's really insignificant. The second question we ask then, could any of these particles remove hydrogen from the solution and act like a base? Well, it's obviously not sodium. Sodium can't react with hydrogen. Can water pick up hydrogen? Sure, but it's such a small amount. The one that I'm actually concerned with is the acetate ion. So we could even go as far as labeling sodium as a spectator. Yes, there are sodium ions present, but they don't do a darn thing. So we could say sodium is a spectator. I'm concerned about that acetate ion. Look at this equation. Acetate is the conjugate base of acetic acid. Can this ion remove hydrogen from the solution? Yes, because look what happens. If there's water present, or any source of hydrogen for that matter, one of these little hydrogen ions can be attracted to the acetate ion. And look what we form. We form acetic acid, which is a weak acid. Weak acids do not dissociate by much at all. So really what I've done is remove hydrogen from the water, and I'm left with hydroxide, which is the sign of a strong base. So of my two products, I get a weak acid, which is really primarily neutral acetic acid molecules. They really don't dissociate and form a lot of hydrogen. They're like 99% neutral molecules, but the other particle formed is hydroxide, which is the sign of a basic solution. The conjugate base of acetic acid, that acetate ion, has the ability to remove hydrogen from the solution. And we kind of mentioned that conjugate bases of weak acids are pretty good bases. They really do have a tendency to shift this thing in reverse. Or in this case, they're going to pick up hydrogen from the water molecules and act like a base. Now, if we wanted to, we could set up a Kb expression. The solution is going to be basic because you've got that hydroxide ion on the product side. If I wanted to set up the equation or the expression for Kb, we would have products. So it would be the acetic acid, H3O2, weak acid, times hydroxide, sign of a strong base, all over just the acetate ion, H3O2 minus. Remember, we do not include the pure water. So here would be my Kb expression. A solution of sodium acetate will be slightly basic. Sodium's a spectator, but that conjugate base, acetate, he's going to remove hydrogen from the water in the solution. And we will be left with hydroxide ions floating around in the water, the remaining water, leaving the solution basic. Now here's what they'll often do. They'll often give us Ka values for acetic acid. So in this case, they're telling me that the Ka for acetic acid is 1.8 times 10 to the negative fifth. But we are not using this as an acidic solution. We're using the acetate ion, the conjugate base, forming a basic solution. So if I need to know the value of Kb, and again, often if you just look at charts, they'll only list acetic acid. They'll list the Ka. So here's where that other equation comes in handy. Again, this is in the AP packet. Ka times Kb equals 10 to the negative 14th. So we're going to have to do this. Again, on a chart, we're probably only going to find acetic acid. Its Ka is 1.8 times 10 to the negative fifth. If we want to solve for Kb, we'll just set the product to 1.0 times 10 to the negative 14th. So we can plug this in our calculator. And let's just do this. That would equal about, 5.56-ish. 5.6 times 10 to the negative 10th. That's going to be pretty common with these solutions. They're probably going to give us Ka values. In this case for acetic acid, very common weak acid. But we're using its conjugate base. So to calculate the value of Kb, we'll just plug it in using this sweet little equation. Ka times Kb equals 10 to the negative 14th.